exploration strategy, and hardly any effort on the model. Both are important.
Yeah.
One hasn't been explored.
So both are important. I will agree with that. And I'm going to focus a bit on this, but I will describe models a bit. Okay, so first, which model am I going to use? Okay, since I'm at the Gaussian process summer school, obviously I'm going to use a Gaussian process. So that's my model section. Okay, maybe that was a bit too glib. So really what I want is some sort of a framework for modeling the uncertainty in my function evaluations. So I want a model, some sort of object that I can make predictions with, and I can measure the uncertainty of those predictions. But there are a number of things that I can do with that. This is not just that I want to get the mean and the posterior. So often when we talk about using Gaussian processes, if we want to implement expected improvement, or we want to implement probability of improvement, UCB, something like that. Since we're using a Gaussian process, it is often the case that we can get away with implementing all of those by just marginally evaluating the posterior mean and the posterior variance or standard deviation. But once we move to different models, there are often a number of different questions that we can ask of that model. We might want, so obviously this prediction, I'm going to return means and variances, but I might want to be able to say, OK, given some inputs x, just sample me values from the function at those inputs. I might be want to say, OK, what are the tail probabilities for that model? What are the quantiles for that model? And the one that I'm going to focus on in this talk, what is the predictive entropy of the model evaluated at a particular point? Okay, but I'll get back to this later in the talk in a number of ways that we can use this and sort of try and generalize the methods that have been talked about and will be talked about later today to a number of different models by sort of saying, OK, given a model, how do we implement these things? So notice that I haven't really, I may have sort of said posterior, but when I said posterior, you could have just, sort of looked at that word a little bit differently and just said, well, that's something that sort of incorporates the data that I've seen so far and gives me some predictions. So I haven't really said Bayesian yet. So one thing that I really want to point out is that what we actually have here, the problem that we're trying to solve, is what I would call a Bandit problem. So this problem where at every iteration, I don't get a sample of all of my inputs. I only get a sample of the particular input that I'm querying. So in fact, if we look at a system where I only have 5 possible inputs that I can query, just a discrete number of inputs, and there's some probability of outputting a 0 or 1, that's the Bernoulli model that Nando talked about earlier. He talked about, I think he talked about beta Bernoulli models. Yeah. OK. So that's just the Bernoulli model. But now I want to have a model that can give me predictions. So a particular model for that would be, in a Bayesian sense, the beta Bernoulli model that Nando talked about earlier. But I could also use a number of frequentist bounds for this type of system. And that's where you tend to get what people call these sort of classical Bandit algorithms, like UCB and things of that nature. But really, those are just some sort of algorithm, some search strategies that make use of frequentist bounds. What I'm going to make use of are Bayesian models of this system. But really, this is the problem. We have the Bandit problem. And then we can talk about what type of model we're going to use to model my latent function. Another thing I want to point out is that really what we have here is a reinforcement learning problem with no transition model. So essentially, a lot of the techniques that you have from reinforcement learning also work in this setting, It's just a little bit simpler because I have no transitions that I have to make. And that actually comes about when you want to sort of optimally solve this problem. You can make use of things like dynamic programming that come from this literature to solve that problem. But that's a really hard problem, so instead I'm going to move to sort of heuristic methods to solve this. OK, so now that I've sort of gotten that out of the way, I'm going to use a Gaussian process. So for the rest of this talk, I'll assume that the model that I'm using is a GP. And this is the only slide on Gaussian processes that I really have because you've seen enough of it already. All right. So now, on to the exploration strategies that I'm going to use. And the first thing I'm going to note is that often in the Bayesian optimization literature and in the community, there's this focus on the acquisition function. And Nando's already talked about that a bit. And I'm also going to focus on an acquisition function, and I'm going to tell you how to construct it and how to optimize it. But really what we have is a policy that takes my model, this M, and the data that I've observed, and gives me a next query point. So one way to implement this sort of querying strategy is to define an acquisition function, or it's sometimes in the Bandit's literature called an index function, and take that, define that, and then optimize that in order to get my query. But a lot of the problems, like the SOO and the BAM SOO models that Nando talked about previously, are actually in this sort of framework. We don't necessarily define an acquisition function. We define a querying strategy. And that querying strategy can make use of the data as it moves from one point to the next. And the reason why it's useful to do this, as Nando's already brought up, is that then we don't necessarily have to optimize this thing at every iteration. So in reinforcement learning, there's also this sort of a distinction, and that's between a policy and a value function. And in some sense, what the acquisition function is doing is it's defining a value function that we will then optimize to construct our policy. But in some situations, both in this community and in the RL community, it's often much easier to define a policy directly. So in fact, if you go back to the sort of the connection between Bandit and Bayesian optimization and reinforcement learning, you can come up with exactly what the value function is, and that is the sort of optimal strategy for solving this system. Although, as I've already pointed out, it's very computationally complex to do this. OK, and in what goes forward, I'm going to then the acquisition function always depends on the current model and the data that I've observed, the collection of x, y input-output pairs. But for the most part, I am going to drop those when I actually write this on the following slides. However, it's important to note that the acquisition function is changing over time and that it actually does depend on these quantities. OK, so Nando talked a bit about Thompson sampling, so I won't really go over this too much, except to say that, first off, if you're working with a discrete model, the first thing you should do is use Thompson sampling, because it's the easiest thing to implement. And the reason that is because really, when we think of this as an acquisition function, it's just sampling a random acquisition function, which happens to be a sample from the model that we're interested in. Or we can view it as this sort of strategy, this exploration strategy, which is randomized over the model to take the max of that model. And so here is sort of the simplest way to implement Thompson sampling. Once we have a model that sort of implements that sample method that I talked about earlier, we just sample from the model and take its argmax. So really, this is the easiest thing you could possibly do. And so here's sort of an illustration of Thompson sampling. This is showing multiple potential Thompson samples. What it's doing is each one of these gray lines is a sample of the function that I'm interested in optimizing. So this is just a sample from my posterior. And so we see that there are sort of multiple modes of this distribution, where the distribution is shown on the right here. And I'm just sampling from this. And the key point is that Thompson sampling is just one single sample. And in some sense, the randomness in Thompson sampling is what gives you the exploration of the function you're interested in querying. And when I move on to the entropy-based methods, we'll see that this is actually a key component of the final acquisition function I'm going to tell you about. So, of course, Thompson sampling, I said it was easy, but in Gaussian processes, it's not quite as simple. And the reason behind this is that I said all you need is a sample of your function that then you can take the maximum of. However, in a Gaussian process, my function is actually this infinite dimensional object. It's an actual function defined over my input space. So one thing, sort of the first thing that you could do, this is the first thing that I thought of when we were looking at Thompson sampling for Gaussian processes, is we just sort of lazily evaluate our function sample f. And so what that means is that every time that I want to optimize my function f, which is what I need to do to evaluate that argmax, I query x, I get its output, and then I add that back into my model with no noise. However, one of the problems with this is that if my problem requires a large number of function evaluations in order to actually optimize this sample, I may potentially have to construct a big kernel matrix in order to evaluate this. So instead, what I'm going to do is I'm going to take my function f and replace that with a feature-based representation. And so what I will describe is a particular feature-based representation, but you could really use anything. And the particular one that I'm going to use are these random Fourier features. And what it really ends up doing is using a vector of cosines evaluated at some matrix transposed with my input x plus some bias term, where then the distribution of this matrix and the bias term b depend on what my kernel for my Gaussian process is. And then once I have that feature, the theta that I need to sample is just determined by Bayesian linear regression. So I end up with just a Gaussian distribution over theta, which then I can sample from. Now, the particular way in which this is constructed involves using Bochner's theorem. And Bochner's theorem is really this first line here. Oh, OK, that jumped me around. OK, it's really this first line here. The first line just says, given a stationary kernel, the kernel is given by this expectation here. And then we can take the exponential here and transform it into a product of two cosines. And then we see that these are the cosines that I split those apart, and that's how I get my features. Where the distribution of W is just the spectral density of my kernel. So you can look it up in Carl's book if you want to use this for any of the kernels that are there. C is just the normalizing constant of the spectral density, because I need this to be an actual distribution. And B is just uniform. And then by stacking together a number of these different cosines, I end up with the features that I stated on the last slide. So this is one particular way to construct this, and I won't talk about any others, but this gives me this feature-based representation that I can then optimize. And that allows me to find a sample of x star. OK, so that was Thompson sampling, which for discrete models is sort of the simplest thing you could do. It's a little bit harder for Gaussian processes. But as Nando's already described, there's a number of other strategies I could use. One I would point out is, so we have EI, PI, UCB. And you can also use mixtures of these different strategies. Because the one thing that we know is that there is an optimal strategy. It's just much too complex to actually compute. Instead, what we're going to do is use a heuristic. But these things are everything that has been described today is a heuristic. So it works in some settings. It does not work in other settings. So instead, what you could do is use a mixture of these and try and sort of learn what is the good strategy as you continue sampling. And so here I say it's not really faith-based because I like that statement there. I'm not really assuming that EI is going to work for my model. I'm not assuming that UCB is going to work for my model or the particular function that I have. I'm going to try and mix between these as I go along. But intuitively, all of these methods try and sort of gain information about the maximum. And these ones in particular do this by sort of giving a bonus, an exploration bonus, to regions of the space that I haven't explored yet. So obviously, if my function evaluations are high in that region, it's a good region. But if my function evaluations are not quite as high, but I really haven't explored that region, this bonus will sort of direct me towards going there. But it may be a better approach, or perhaps a more principled approach, to directly sort of look at the information I would gain by querying different locations. And so this was brought up yesterday in the setting of active learning, where I'm trying to learn about some function f by saying, OK, if I query x, what is my entropy going to be about the function after including that new query point? And I need to take this expectation here because I haven't actually seen this point y yet. OK, so this will result in selecting the point that gives me the greatest reduction in entropy about my function f. Now, this is a little bit difficult to do in practice because if I do this with a non-parametric model for f, f is going to be a Gaussian process. So evaluating that entropy can be hard. And that sort of brings about a number of the methods that were discussed yesterday. And this work goes back to a lot of different places, but especially the paper of Mackay, or one of the papers of Mackay in 1992. There were like 3 or 4, 5, I don't know, quite a few of them in that area. But there will be citations at the end, so you can find this particular one. OK. But I'm not interested in actually learning the function f well. All I care about is finding the maximizer of the function f. So instead, what I can do, my function f is this latent variable. So I also have a distribution over the maximizer of my function. So what I can do is look at the entropy in the maximizer, x star. And on the previous slide, I also introduced this. So this, by the way, has been done before, this looking at the entropy in this way. Villemontier did this in 2009, but his method required you to discretize the space in order to solve for the particular point x. Philip did some work on this in 2012, which eliminated that sort of restriction. You could work with continuous spaces and not have to discretize the space. And there are some pretty hairy approximations there. So instead, what we're doing is, by introducing this additional term, which we see doesn't depend on x, we still have the same acquisition function. But now, the nice thing about this is that this quantity is the mutual information between my observation y and the maximizer x star. The great thing about that is that the mutual information is symmetric. So this is the mutual information in one direction. between y and x star, or it might be the other way around. I actually can't remember. This one is it in the other direction. But again, these two are equivalent. The nice thing about this reformulation is that now we have, on the left side, we have an entropy of y given my data. This is just the predictive entropy for outputs in my model. And in fact, when I use a Gaussian process with a Gaussian likelihood, this is going to be a closed form calculation. And then on the right-hand side, I have this expectation over x star, and then the entropy, which now the entropy is over predictions, which is good for me. We'll show a method that efficiently approximates this, conditioned on x star. OK. So, and in what follows, I'm going to drop this data term just to make the equations a little bit easier. OK. So up at the top here, I've just rewritten this acquisition function. And the first thing we're going to do is approximate the expectation with Monte Carlo. So I need to sample x star. And then if I assume that the distribution of yx and the distribution of yx given x star, if I assume that those are Gaussians, then I have this nice form right here for this acquisition function. Now, this is just the variance that my Gaussian process gives to me. So all I have to do is compute predictions with the Gaussian process, get the variance, and then this is the variance of my input x conditioned on the fact that x star is a maximizer. So this one, obviously, I know that this is Gaussian. This one is not Gaussian. So instead, what I'm going to do is I will ultimately end up with a Gaussian approximation for this distribution. And that allows me to perform this calculation. And all I have to do is take the difference of two variances. And that is my acquisition function. So the two steps are sample x star. But now you see the reason why I talked about Thompson sampling earlier, because this is just Thompson sampling. All I have to do is sample locations x star using the Thompson sampling scheme introduced earlier, and then plug them into this Monte Carlo approximation. And then, given those x stars, I have to approximate this distribution with a Gaussian. OK, so how do I approximate this with a Gaussian? Well, that's a good question. I have to make a number of assumptions about sort of what it means for x star to be a maximum. And so this is going to be approximate. So the first, I'm basically going to assume that, and I will go into these little boxes in a bit more detail in the next few slides, but I have to assume that f of x star is a local maximizer. So this essentially involves some assumptions on the gradients and the second derivatives of the function at x star. But for the most part, those just correspond to gradient observations in a Gaussian process, which can be done in closed form. So this distribution right here, I start with a Gaussian over f of x star. I end up with a Gaussian over f of x star, which is a closed form computation. OK. The next thing that I need to do is I'm going to assume that f of x star is greater than all of the observations that I've made so far. Now, this cannot be done in closed form. What I'm going to have to use is expectation propagation in order to evaluate this and end up with a Gaussian approximation to that. I'm not going to go over how to actually derive the EP algorithm for this. But we can talk about that offline if you're interested. OK, so then, given that, I'll end up with a Gaussian distribution over f of x star. Now, these two parts can be done before I query any point. So when I go to evaluate and maximize my acquisition function, I do this work. And this is where most of the work lies. And I do that before I have to optimize it. Now, once it comes time to optimize it, I just have to include one additional constraint. I'm assuming that f of x star is greater than f of x at the particular input that I evaluate. Now, that's going to be end up with a Gaussian approximation. And that Gaussian approximation, we will see, is quite easy to do. Most of the meat is here, but this can be done before we actually have to evaluate any x. And then this gives me my Gaussian approximation to f of x conditioned on these three things. And then this variance here is the variance that I need in the previous slide. So then I can take the difference of these two variances and end up with predictive entropy search, our method. OK, so a bit more detail in how we do this. These are the sets of constraints that I'm really assuming about my system here. So I'm assuming that so the first of these two really say that f of x star is sort of a local maximizer, or a and this component right here. So this is just saying that the gradients are 0. I'm going to assume that the off-diagonal components in my second derivatives at x star are 0. We can also vary this a little bit, but that seems to work reasonably. And then that, so I want this to be a local maximizer, so I need to say something about the curvature. So I'm assuming that the diagonal components are less than 0. OK, so these first two can be done in closed form. That's just gradient observations for a Gaussian process. There's a good paper of Carl's that tells you exactly how to do this. This one right here, since it's not an equality, but it's an inequality, that is why we have to use EP. And same for this component right here. And finally, for C, we're assuming that f of x star is greater than f of x. This is another inequality, so we have to essentially use EP as well. But because we only have one step right here, it's not really EP. It's moment matching, and this is quite simple. So the first right here is just exactly what I said earlier. Incorporate those constraints using gradient observations, and we get out a Gaussian for f of x star and that diagonal component right up there. And I'm going to call that z. And then we have to incorporate the next set of constraints approximately. So really what we're doing is we're taking this distribution over f of x star and the diagonal of the second derivatives and multiplying by some different factors which attempt to incorporate these constraints. So these constraints right here correspond to the constraints on the second derivatives. So I'm just saying that I have a product here of indicators that say that my diagonal components have to be less than 0. And then right here, I have this maximizer constraint, which is saying that f of x star has to be less than f of x. However, I never actually observe f of x. I only have observations about in the actual observation space, my y's from my data. So instead, what I'm going to do is I'm going to say that f of x star has to be greater than the largest y that I've observed. And I'm going to soften this constraint by the noise level of my Gaussian process. And this will actually come up as sort of a problem with predictive entropy search a bit later. And I'll show you how to eliminate this as well. OK? But then we incorporate these constraints using EP, which is a method that is designed to exactly work with these sort of factors. And we end up with, that should be V1 right there. But we end up with a Gaussian distribution over my latent variables. And then what I can do is incorporate this final constraint, which is just an additional factor, an additional indicator factor. But again, we essentially use EP. But EP is an iterative algorithm, if you know anything about EP. And if you don't, come ask me about it later. But it's an iterative algorithm which continually replaces factors with approximate factors. Now, the problem with that, or not really a problem, but one of the results of that is that you have to go over each of the factors multiple times. However, since we have only one factor here, it's not even really EP. It's just we have to incorporate one single factor, which it actually ends up being just simple moment matching. So this constraint is just a simple, you have to take a few maxes in this situation. No, just add a few variables together here. It's a few summations. So this is easy to evaluate. So the first two involve EP. We do that before we optimize our acquisition function. And then during optimization of our acquisition function, we have a little bit of extra computation that we have to do for this C constraint right here, the C factor. OK, so really, though, but what does this look like? So in blue here, I've shown the results of just the Gaussian process given the current data that I have about the system. And then what I'm going to do right here is that at x star, I'm going to make an observation that x star is actually the location of my maximizer. So in green, we have the sort of, if you will, the posterior after conditioning on x star. And in blue, we see the posterior, or the prior before conditioning on x star. So what this means is that if you look here, these sort of perfectly overlap. So what you really see is that around the location of the maximizer, and this is the thing that I sampled using Thompson sampling, it sort of just pulls up the distribution. It pulls the distribution up, and it may push the distribution down in some other areas. In order to result in this approximation. And so really what we end up seeing is that this thing, because of the way that it works, is actually quite well approximated using a Gaussian, which is good because that's exactly what EP is doing. So of course, it's nice to look at this and see what the conditional approximation does. But we're actually interested in sort of how well this is used in order to evaluate our acquisition function. And so one of the things we looked at is we looked at seeing, OK, we can actually, if we do a lot of computation, basically grid up our space very, very finely, we can exactly compute the acquisition function. And that is this point, or this graph on the left. This graph in the middle is the entropy search approximation using Phillips' method. And this one on the right is our predictive entropy search method. And we see that this actually does quite a bit better job of approximating the sort of the ground truth, if you will, for this acquisition function. And one thing that's interesting to note is that this point right here, I don't think you can, especially you at the back, I apologize. This may be hard to see, but I have an observed data point right here. I have an observed data point right here that sort of actually happens to be the best point that I've seen so far. So what you actually see is there's a dip. There's sort of a bowl centered around this data point. And we don't really see this in the ground truth. And there's a reason for that. So it actually, what? Oh, sorry. So we've actually seen some data here. So it's actually not that great to put a point very, very close to this. And this depends on the length scales of the kernel you're using. But you can get a lot more information by deviating a little bit from the best point that you've seen so far. This is actually true. The only reason we didn't see this in our ground truth is essentially because we didn't grid the space up fine enough. And we actually had to allow our computation to complete so we could submit the paper. So it's almost as if our approximation is doing better than our ground truth. It is actually capturing reality a bit more. And I really say that because, of course, this ground truth uses a much more computationally complex approximation that we just couldn't make fine enough in order to actually get this figure done. OK, so of course, that shows how well this works on on actually capturing the acquisition function, on approximating the acquisition function. But the next question is, how well does this work on real-world tasks? And the one thing we see is that it consistently outperforms the entropy search approximation, mainly because of exactly what I showed on the previous slide. It does a better job of actually approximating this, this acquisition function. But we also see that in many scenarios, it does better than other acquisition functions, such as expected improvement. So there are some situations where, notably, this function and this function, where expected improvement does quite a bit better. And really, the reason behind that is that this is a robotic walker. We basically have a biped that we can adjust the parameters of, and we see how far it walks before falling over. This function right here is this, I believe this is the Hartman 6 function. So it's a 6-dimensional function that we're trying to optimize. However, this function is actually, it's quite smooth. It's not too difficult. Actually, that one, I can't remember if this one is the 3-dimensional version or the 6-dimensional version. But you see similar results. The function itself is somewhat smooth. And so methods that are a bit more greedy are able to find a point that's relatively good and just stick with that point. And they don't, once they find a point that's relatively good, they don't really deviate from this. Which, if you have a function that is high dimensional and relatively smooth, that sort of greediness actually helps you, and which is what we see here. And similar things happen with this walker. However, we also did this experiment where we increased the amount of noise in the system. So this was using a very small amount of observation noise. This is using a large amount of observation noise. And what we see here is that predictive entropy search is able to do much better, because essentially what happens is expected improvement finds a region that it thinks is pretty good, and then again, because it's greedy, it just sort of stays there. And it doesn't really explore. But really, the noise is tricking it into thinking that this location is actually a good location. And since it stops exploring, it sort of plateaus out. Whereas predictive entropy search, because it does more exploration, is able to find a much better point. So really, and this may get back to what Nando said earlier about faith-based, that the method of selecting between different acquisition points. In some sense, part of the faith is if you think that your function is relatively easy and high dimensional, you should probably do something like expected improvement. If you have a hard function and you're really interested in finding the maximizer, try something like entropy search. So we've also done some extensions to this, some extensions to the constrained problem, which Nando brought up. So here, I not only have a black box function that I want to optimize, but I also have some constraints that are black boxes as well. OK? And so what we end up seeing is that we can derive predictive entropy search for this model, and we end up with a very similar looking acquisition strategy. And however, here, the entropy that we're looking at, these y's, I've collected all of the function evaluations and all of the constraint evaluations into a single vector. So this entropy is actually over a multivariate Gaussian. So our approximation has to differ slightly, but the high-level point for the approximation of sort of constraining on what it means for x star to be a maximizer and using that to constrain y, and also approximating this expectation with Thompson sampling, this sort of the high-level view of predictive entropy search with constraints remains much the same. And so I won't go into the details about how to do these computations. But here are some examples of it running. On the left, we have a neural network that I'm trying to tune subject to the constraint that I want it to be fast. So the sort of parameters that I have are the depth of the neural network, the width of the neural network, the tanh or ReLU that I use, all sorts of things that Nando talked about earlier. But then I also have this constraint that I don't really care about how fast the neural network is, so long as when I go to test time, its predictions are under 2 milliseconds. So let's say that I wanted to take this neural network and put it on a smartwatch or something like that. Although, frankly, the smartwatches are probably better than the first computer I had. So it's probably fast enough. But anyways, let's assume that I have some really restrictive computing environment. And we see that predictive entropy search does much better than expected improvement with constraints, which is the constraint method that Nando talked about earlier. There are some actual fundamental reasons why EIC, expected improvement with constraints, is not able to perform as well. And it really comes down to the fact that it is not allowed to query points that it is fairly certain are either low valued or that are violating the constraints. Whereas predictive entropy search can query points that it knows has low values or it knows are violating its constraints in order to gain more information about either the function or the constraints. Here we also have, we're tuning Hamiltonian Monte Carlo subject to constraints on that it has to pass a number of convergence diagnostics. And we see similar results, although the error bars here don't overlap, but they're much bigger in this sort of model, especially for EIC. It tends to get stuck in this system and either be good or really poor. OK, so what are some problems with predictive entropy search? Well, one of the problems I noted earlier was that inside our approximation, we're assuming implicitly that our observations are Gaussian. We're assuming that our observations are Gaussian in order to make that sort of softmax constraint. However, this is a problem if I then want to move to models where I don't assume a Gaussian likelihood. And this is sort of fundamental to how we do predictive entropy search. Another problem with predictive entropy search. Well, what I'm really looking at, the thing that I'm interested in optimizing is the entropy of x star, the entropy of the location of my maximizer. However, I could consider optimizing, and I believe this was brought up yesterday as well, a space where I really have a union over disjoint spaces. So I might be, and this is sort of a first step in making sure that this works for the sort of conditional spaces that Nando talked about. But here I might be optimizing something where I have a regression method, which is an SVM with 3 parameters, or a neural network with 7 parameters. And so I want to compare these two things. Part of the problem is that the entropy over a space of this form is not well defined. So I'm sort of starting from a problem that is sort of incorrect in some sense if I want to use entropy search here. OK, well, of course, I brought up these problems for a reason, and that is because here's a potential way to solve this. And this work is unpublished yet, and it's still getting tweaked. So I won't go into too many of the details. But the main idea is, OK, rather than using x star, I want to use f star. So I really think about this. It's sort of the same thing as going from Riemannian to Lebesgue integration. I'm replacing something in the input space with something in my output space. And now the nice thing about this is that now my f's are this nice scalar function, and I can include those constraints in a straightforward way. And it also, the high level looks very similar. But now I'm saying that f star has to be greater than f of x and greater than the point. This can be computed before I do my optimization. And the details of the approximation are different. but it now allows me to handle both of the sort of problems that I introduced earlier. And this is an illustration of sort of what this looks like. So rather than conditioning on a point being a maximizer, I'm now conditioning on an output point being a maximizer. And it squashes my function and squashes my posterior in a different way, but it still ends up being well approximated by a Gaussian, which is, again, nice, because that's what we're doing. And sort of early results indicate that and we're running more results on this right now, that it is just as good as predictive entropy search in problems where predictive entropy search applies. So that's in sort of this region right here. This is just optimizing a 2D function, just standard. But in problems where predictive entropy search does not work, it also tends to outperform things like EI and PI and other methods, which are, so it exactly works in the situations where PES does, and it improves upon other methods where PES does not. So finally, I'm just going to give a few words here. Earlier, I talked about having models and sort of defining interfaces for models to be able to work with these different sort of methods. And I'm trying to sort of deviate from just using Gaussian processes. So, of course, we have implemented most of this work in a package we call PyBo, which you can find here and talk to me about it later if you're interested. But of course, since I'm going to talk about this package, if you just want to use it, you don't really have to think about things. But so you just call a solver with f and some bounds. We haven't really implemented the unbounded things. So this is joint work with Bobak-Shahari, who worked with Nando on the unbounded Bayesian optimization. But we haven't really implemented that in this framework yet. But we can also vary all of the policy you want to use, the initialization method you want to use, the solver you want to use if you're using an acquisition function. We've also got some work that replaces this method with sort of the direct policy-based method that I talked about. But of course, I can also specify what my model is. So the earlier version, just it figured out the model I want to use based on some data. We can also specify the model. We can replace a model with a different model that does MCMC. We can do SMC. We can actually implement all of these sort of optimization-based methods that Nando talked about earlier. We can implement more complicated models. In fact, you could use, we don't use GPy here, but you could use GPy in this sort of framework. And finally, you could sort of insert yourself into the loop, which is how we do, this is just a simple loop, which then, I don't know why that didn't, which you can view these things. There's also a 2D animation and some things like that I can show you earlier. And the final thing I wanted to leave you with is, so we also have implemented Bandit models. So this is which work directly in this framework. This is the Bandit, the Beta Bernoulli model that Nando talked about earlier. But usually people don't use things like expected improvement or probability of improvement with bandits. The bandits people don't really like or know or understand these models. But you can use them here. So this is using, I think this is using expected improvement. However, there may be a reason why the bandits people don't use expected improvement. And that is because you tend to run into situations like this, where especially when you have independent models, and these are just the means and, I think in this case, quantiles of each of the individual arms that I'm dealing with. When you have models like this, often you can get expected improvement gets quite stuck in these types of models. So in fact, right here is the optimal parameter. This one is relatively good, but it's not as good as this one. But expected improvement has said, OK, that model is good, and I am never going to leave it. And so I could basically run this to infinity, and expected improvement is never going to try that. So yeah, this is, in fact, one of those situations where the acquisition function and the model do sort of matter in conjunction. And I'm going to stop before Nando yells at me. So thank you.
Maybe one quick question, if there's one. Yes.
Yeah.
Back on your slide where PES and EI are compared in a noisy case.
Yeah. Yeah.
Very noisy case with the
Oh, OK. Yeah, the walker. Yeah. Yeah.
Yes.
Here.
Which variant of the EI did you use for coping with noisy observations?
We compare against the maximum incumbent, where the incumbent is defined as the, I believe in this case, the maximizer over the posterior mean. And then we varied so there's the offset parameter in expected improvement. We varied that a little bit to get good performance. But yeah, it's sort of the standard thing to do when, yeah.
EI is not meant originally to deal
Well, so it's not originally meant to deal with that. We personally and a number of other people have, we generally tend to assume noisy models, and we compare against the maximizer of the posterior, typically. Although, in fact, in our system, you can define arbitrary targets, which hopefully we'll hear more about later. Yeah. Okay.
A really quick question for me. For this final example with your bandits, did you try this with entropy search as well?
Yeah, entropy search works better. Yeah.
Great. Then let's thank Matthew. Oh, sorry.
Although I should point out though that you for this type of model you don't need to do all the approximations that we need, and so entropy search ends up being the same thing as Iago. So yeah. Yeah, so this is actually predictive entropy search using a variant that was slightly, so in fact in Philip's code, and in Philip's method and Philip's code, there was an additional expectation that he did in a slightly different way than, once you define PES in the way that we did, sort of taking the expectations over hyperparameters and things like that is straightforward. That one is more along the lines of what Philip did. And so you would, with PES, you wouldn't necessarily use this PES NB. That's for, I think it's naive Bayes, but not like naive Bayes, but a naive Bayesian way or something like that. Because predictive entropy search is straightforward to extend to this sort of approach, you would never use that. But we wanted to see if that contributed at all to the sort of differences we saw between our method and Philip's. And we see that there does seem to be a little bit of a difference here, but it's not much. And so I would say always use PES, which is what we do.
Now we should really.
It's very quick, actually, I think. What's like in practice?
Yeah.
Constraints for the dimensionality of the problem you can solve with predictive entropy search?
So the main problem with higher dimensions is, of course, then how many points you need to evaluate. So in higher dimensions, you always need to evaluate more points. So you can always apply these methods and then do something like an approximation to the Gaussian process to deal with many more points, or you could easily incorporate this with something like the random embeddings that Nando did. So straightforwardly, I'd say 10, 20, getting to 30, things start to get hard. But then basically, it depends on your model. If you just have a Gaussian process with a squared exponential, sort of what you're going to end up seeing is you don't use a grid, but you end up seeing grid-like behavior because evaluating a point really just pokes down the variance at different locations until you get enough points. You just sort of grid-like poke down the variance.
Because you're already eating into lunch
Yeah.
and Mark's time. Let's thank Matt again.
I'm going to run over anyways.